All right. Let's get started. Hey everyone, how are you guys? Hopefully you're all well. Let's actually jump into it. I have a feeling I'm forgetting something, but I don't know. All right, so first thing, some updates in terms of the exam and how it's going to be and all that good stuff. This view is really weird. Okay, so yeah, in terms of the exam, like I said, it should be the end of next week. So technically, you do kind of have 2 weeks. I would probably run some sort of a mock exam for the first exam at the end of this week, just to see if, just make sure that you guys can get the technology to run properly. So when I post the mock exam, I'll probably actually have you guys go through the motions of trying to submit it online to make sure that next week everything is going to be fine. Also, in terms of how it's going to be administered, so I spoke to a lot of people. I think I sent an email about this, but I don't remember, so I'll just mention it again. I spoke to the guys who are going to help me administer the exam online, and the original solution I was thinking of working, technically it can't work, and so we came up with another idea that I think should work fine. And so what we're going to do is he's going to make sure, well, that we know will work, but he'll have to get permission from his supervisor to actually implement it. So, and we're pretty sure it'll be fine. So I will get the details from him about that tomorrow, I think. Okay, so that being said, as I mentioned, it's going to be something like, the exam is going to be like a PDF or something, and you're just going to take it and then scan it and send it to me. Essentially is the idea. But there's going to be a proctoring component to it, which I think would involve you needing a webcam. And I'm pretty sure this is going back to a question that was asked earlier in the chat, that your phone can be used as the webcam. And of course, as I mentioned, privacy concerns and all that, taking it very seriously. The software that we are used is approved by FERPA, F-E-R-P-A. I don't remember what the acronym stands for, but it's basically a federal law that talks about the privacy of student records and all that good stuff. So don't feel too creeped out about this. I'm definitely going to have you protect all your privacy, but there has to be some way of oversight here. That being said, I do have to change the format in which I wrote the test before, so I will post the mock test for the first test either tonight. I might have to go shopping later, but either tonight or early tomorrow. So you'll see an example of what the test would look like. So again, I guess there's more details that would follow, and I'll probably tell my class tomorrow what that's going to be. That being said, I don't want you guys to freak out. The mock exam this week, even if you don't do well on that, you'll know exactly what you need to fix for the following week, because I'm going to make it look very similar to what the exam is. I mean, with all that's going on, we don't need any extra stress. Does what have a due date? Yeah, so the mock is going to be like at the end of this week. So you can do it like Thursday or Friday or whatever you have time. But what I'll do is whenever we're going to do it, I will put like a strict timeline on it. And the first test will be Wednesday next week. So that's like the 29th for you guys. Yeah, so the time would be just like it's in an actual class. So it'll be like an hour and a half exam, hour and 15 to hour and a half, something like that. All right. So as I said, and I'll post the mock exam on the class webpage. Once it's actually up, I will send you guys the link. So that is how things are going in terms of exams. Was there any other updates I wanted? Yes, and I also mentioned to you guys, so yeah, it's official. The final exam will be online. It is going to be departmental for everybody. So whether you're in my GH class or my my RS2 class, whether you're my Monday, Wednesday, or my Tuesday, Friday, I'm not writing your final. It's going to be done online. It is going to be done through Blackboard. So you guys should probably check now that you're all able to actually sign into Blackboard and actually move around. So that is, yes, well, grading is going to be, grading, I'm not totally sure on grading because this just came down on, like when I sent you guys the email about, oh, by the way, now I just found out that finals are going to be online. It was literally a few minutes before I got the email myself. I got the email like, oh, and I immediately forwarded it to you guys. And so I really don't know what the format is going to be like, but if it's going to be through Blackboard, I'm assuming it's going to be a combination of short answers and multiple choice. I really don't see another way of them administering it on Blackboard, because there is usually, and this is one of the things I just know about Blackboard, there might be storing issues on like everyone sending in scans of finals. It's going to be really crazy. So I'm imagining that the final is going to have a somewhat different format, but I do not know for sure right now. If it is the case that it is short answer or multiple choice, then I wouldn't have to grade it. The computer would actually grade it automatically. So, but like I said, I just know that it's definitely going to be online. It's definitely going to be through Blackboard. In terms of format and how it's going to be graded, I do not yet know. But the moment I do, I will definitely kind of reach out to you guys. So the mock test is going to be about 6 problems. So my test is going to be about 6. And I'll throw in some bonus problems. Yeah. So the bonus would be on material that I've taught since the material for test 1. So like the stuff we're doing now. Maybe I'll throw in some questions about parametric equations or vectors as the bonus. But I would definitely focus on everything to the end of series. You might even run out of time before you hit the bonus, so you better finish everything else. Nicholas missed everything. Well, this is being recorded. Let me double check. Yes, it's recorded. So I guess just wait until I post it. So yeah, the shortcut is mock test for test 1 is going to be posted on the class website. It will be up by tomorrow, the latest, because I have to slightly change the format. The plan for how it's going to be administered has to slightly change, and I will get more information on that tomorrow. Final exam is going to be done online. It will be done through Blackboard. I do not yet know the format, and it's going to be not written by me. It's going to be departmental. Yeah, in terms of the important things, yeah, the mock exam, I'll probably do a fake administration of the exam at the end of this week, and then your actual exam is next week. So for you guys, I believe it's the 29th of April, and for the Tuesday section will be the 30th of April. That being said, if you guys want to take a test with the Tuesday section, I wouldn't really care, actually. So yeah. Yeah, well, you can't take both. Okay. Yeah, I think that is it. So let's actually get the show on the road. For the most part today, should be a short lecture, but we don't know. I might get excited and go off on tangents, but I'll try to rein it in, because it's really cool stuff. We're not going to talk about a lot, but there's a lot of geometry and intuition I want to talk about that goes behind the scenes here. And so I'll talk about some of that, but we are basically going to look at some more about vectors as well as the dot product and the cross product. That is the plan for today. And those two things are very cool and very important. And let me share one note with you guys. And as usual, I am going to stop showing video because I want to minimize the amount of glitchiness going on. So you guys will now listen to the soothing sounds of my voice talking math. Okay. All right, so this is vectors. This is something that we covered last time. So we saw what a vector is and what it means to scale one, how we can write it down, what it means to take the negative of a vector, the magnitude of a vector, all that good stuff. A lot of you guys seem comfortable with this. I believe that a lot of you knew about vectors from last time, how you add two vectors together, how you'd subtract a vector from another one, and all that good stuff. Properties of vectors, knowing that two vectors are parallel if one is a scalar multiple of the other one. We did a bunch of examples of combining vectors and just doing a few arithmetic type operations on vectors, so that's good. Next thing I want to talk about is the standard basis vectors. These guys are known as E sub I, but that's really in more abstract math circles. Engineers and all the other people who don't go very far in math would know them as I, J, and K. We're going to talk about the I, J, and K vectors. So what these vectors are, these are going to be guys that are running along the axes. So more specifically, let's grab my pen here. So if I have the axes, remember we draw it in this view here. So this is the X, this is the Y, and this is the Z. If you imagine that there are some vectors, so there's a vector that's running along the X. That has magnitude 1, so it'll hit the point 1 here. That is the vector that we call I, or I hat. Then there's another vector that's running along the Y. Starts with position the origin. Also has magnitude 1, so it goes 1 on the Y. That guy we call J. Or J hat. You write a little arrow over these because these do represent vectors. And then there's the other guy running along the Z axis. So that's going up. So it's a position vector. The initial point is the origin. It also will hit 1, and we call that vector K. These guys are the standard basis vectors, and they are extremely important, extremely useful. And I want to realize that these guys are kind of units. Well, let's not go down that road. Notation-wise, this actually allows us to express vectors in another form, which for a lot of proofs and a lot of things that we'll want to do, it might be useful to actually express the vectors in this form. So what I want you to notice from in this situation is that suppose I have a vector A, which is A1, A2, A3, right? So a vector in 3 dimensions. What I want you to appreciate is that this can be written as, by the properties of vectors that we discussed last time, A1 times the vector 1, 0, 0, plus A2 times the vector 0, 1, 0, plus A3 times the vector 0, 0, 1. Okay, now we know about scalar multiplication. This is just A1 times all of these guys, and so that's just the vector A1, 0, 0. This is the vector 0, A2, 0. This is the vector 0, 0, A3, and we can add them all up to get that guy. And these guys here are our vectors I, J, and K. So a vector can be written in 2 forms. This is another way to express J, to express the vector A. So this is the IJK notation. And this guy here is often called, well, they're both sometimes called that, but the component notation. Okay. So of course, if you're in R2, which it's worth mentioning here, even though we're not going to be working R2 a lot, I is just 1, 0, and J is just 0, 1. There are only two to worry about, the guy running along the X and running along the Y. In 3D, it's I, J, and K. Of course, once you go 4D or higher, we use E sub 1, E sub 2, E sub 3. So this I would be E sub 1, J would be E sub 2, K would be E sub 3, another axis would be E sub 4, and this is called the basis vectors. And that language kind of comes from linear algebra, because you can express any vector in terms of I, J, and K, right? So this is called a linear combination of I, J, and K. L-I-N. Well, okay, so, and there is this thing in linear algebra that talks about basis vectors and being a linear, you can express any vector in a space as a linear combination of a bunch of guys, then it's called a basis with some other conditions being filled in. Let's not worry about that. So I just want to introduce to you that there's another way that we can write vectors. So for example, I can write the vector 1, 2, -3 is the same as well, I plus 2j minus 3k. Right? And these two things mean exactly the same thing. One thing I want you to notice, though, is don't mix notations. Which means if you were to do something like I, comma, 2j, comma, minus 3k, and put brackets around that, that is wrong. That is meaningless. It doesn't make any sense. Either you do the IJK notation or you do the coordinate component notation. You do not mix them. So once you are putting this, you don't put parentheses and commas. If you're doing this, you don't put addition signs in between, and so on and so forth. Do not mix the notations. One is writing it as a sum of I, J, and K, where they have coefficients in front of them. One is writing it as a coordinate with sharp brackets. You do not do both. So don't mix them. It doesn't make any sense. That's not the notation. Okay, so that's I, J, and K. They're going to be very important. We're going to be using them even later today. Another thing I want you guys to know about is something that's called a unit vector. Now, a unit vector is simply a vector of length 1. That's it. That's what makes a unit vector. Now, if you have a non-zero vector, then a vector that is in the same direction as A, and it's a unit vector, this guy has this formula. So let's make that a little bigger. This guy has that formula. So you take A and you're going to divide it by the length of A. So this pretty much says if you try to find the magnitude of this, you'll find the magnitude of this over that number. It'll actually cancel out and give you 1. So that's how you can find a unit vector. So for example, if I were to ask you, find 2 unit vectors that are parallel to this vector, right? So let's say that's the question. Find 2 unit vectors that are parallel to that vector. Well, the first thing I would do is I would find the magnitude of A. How do we find the magnitude of A? This is where you guys come in. Someone chime in. Distance formula, but what does it look like? Square root of the sum of a's? No. Yes, the square root of the sum of the squares of the components. So you take the first component squared, add it to the second component squared, add it to the third component squared. And yes, that is something that you can derive from the distance formula if you just imagine that this vector is a position vector. So that's going to be the square root of 4 plus 1 plus 9, which is the square root of 14, which means one possibility for you is going to be the vector 2 comma minus 1 comma 3 divided by the square root of 14. Or in other words, I can write this as 2 over the square root of 14 comma minus 1 over the square root of 14 comma 3 over the square root of 14. And then you can realize the other, I asked for 2, would just be the negative of that. Now we know that two vectors are parallel if they are scalar multiples of each other. The thing is, what scalar would you multiply this by to make sure that the other vector is a unit vector? Well, -1 is what you want to do. You don't want to actually scale it, stretch it, or shrink it by anything. Just take the negative to go into the other direction. So these are your answers right here. So this vector and that vector are vectors that have the same direction as A, meaning they'll be pointing in the same direction, but they have a magnitude of 1. A itself has a magnitude of radical 14, which is bigger than 1. So essentially you'll have, that's your A, and then you'll have another vector on top of that. Running in the same direction, that is the vector u. And the length of u is 1. And then, of course, you'd have negative u, which is pretty much the unit vector going back the other way. That would be minus u. Okay, and those would be parallel because they're running along the same line. Okay. So same direction is how we think of as parallel. Technically, going backwards is sometimes called anti-parallel, but you guys just can know it as parallel. And that's that. The standard basis vectors, I, J, K, very important, as well as the idea of a unit vector. Unit vectors are going to be very important because a lot of times we want to be able to point in a direction in such a way that it's not scaling anything, because sometimes we're going to develop things and derive formulas that it's going to depend on a certain direction, and you'd have to multiply it by some other formula, but you don't want to actually scale the other formula by any amount. You want to essentially the magnitude to scale by 1. And so the unit vector is very useful in keeping things tight and not having things blow out of proportion. So that's important. And that is the end of this section. Okay. Any questions so far? So these are pretty much definitions that you need to know. Yeah, that was it. So this is actually just me finishing up the last lecture, which we ran out of time last time. Yeah, so IJK, these are called basis vectors. These are the guys that run along the axes. They are unit vectors themselves. Now you know another name for them. Because multiplying by a constant scales the vector. Okay, so remember that So someone asked, why can't we multiply by a constant? Because if you have a vector and you multiply by a constant, in general, you would scale the vector. You can stretch it and move it. Sometimes you want to point in the same direction, but you don't want to stretch or shrink anything. So multiplying by 1 keeps that safe. So sometimes you don't want to be, while you're multiplying by a vector, you don't want to stretch anything else, okay? So you want to keep everything tight, everything in, just if you want to just point in a direction, but you don't want that to involve scaling of any sort, a unit vector is how you're going to do it, right? And so unit vectors are important in that regard. So this brings us to the next thing that we're going to want to talk about. The dot product. Okay, so before the dot product, let's actually talk about some motivation. So I'm going to define the dot product and the cross product to you guys, but I do want to kind of not just give you the definitions. They have their own little elegance to them and their own little mnemonic and their own little patterns to them. But I want you to kind of see where they're coming from, why they're important. Why did we define them the way we actually define them? So I do want to give a little bit of a background here before we actually go into the nitty gritty. So some of that we've been seeing in last lecture and the lecture before that. 3D has some challenges, and there are a lot of things that are different in 2D. So for example, in 2D, x equals 1 is a line, while in 3D, it's now a plane, right? So clearly the notation, everything is going to change. The equations of certain objects that we knew in 3D that were curves, they're now actually planes and cylinders in 3D, and all this sort of, things change, things are different. The 3D world is different. And not only is it different in terms of how we want to look at things and locate things and how we want to conceptualize things, but straight up down to the notation is going to be different. So we are going to need different ways to look at old notations and old ideas in ways that are more amenable to the three-dimensional case or even higher, right? So when we come to calculus specifically, talking about calculus specifically, there are some important ideas, right? So there was the idea of, what were the important things in calculus? The derivative and the integral, right? And of course we need limits to get these guys to actually work out and behave. But the derivative and the integral, think about what you had to do to even create an integral. You had to create a Riemann sum. This involved you looking at one of the axes, the independent axis. You take an interval that you're interested in, and what did you have to do? You had to slice it up into smaller pieces, into sub-intervals, right? So you have all these little things. Now, one thing that's also important in that was that you had to figure out the length of the subintervals. This was the guy that's called delta x. So we need a notion of magnitude of one of the axes or on one of the things that we're taking as the independent input. And we need a way to actually slice it up into chunks. So that's going to be important. Now, once you go into 3D, a lot of times we're going to be in a situation where our inputs are going to be regions in the XY plane. So I'm going to have an X coordinate and a Y coordinate that I'm plugging into something to get some formula to pop out. So for example, this guy over here, this will be something like Z equals some function of X and Y, right? And we'll talk about objects like this later on. So this you can actually think of as it's some function where the inputs are both X and Y. And you might wonder if you're in the XY plane, there's going to be a region of all these coordinates that you want to plug in to this function to have some sort of output. So now the idea is, if this is like our input, it's kind of like our x-axis in the 2D case. This is where our inputs are coming from to look at something else. We would want to think, well, how are we going to dissect this input and put Riemann sums on it and all that good stuff? Now, the details of all that you're going to cover in Calculus 3, so I'm not going to talk about that. But I just want you guys to get the idea that in the same way that we needed to be able to dissect one-dimensional things in Calc 1, we will be needing to dissect two-dimensional things in Calc 3 and dissecting three-dimensional things in Calc 3 and higher as well. What that comes down to is this little idea of doing patches, right? So we can slice things in two directions, and then we have these little patches, and that we can think of as the dissection. So instead of having a subinterval with a certain length, we are going to have a patch with a certain area. And this is how we're going to slice things up. So now other things start to come into play, and we're going to want to know how to measure the area of a patch, right? How to measure the angle of the patch itself and all that good stuff. That's going to need to come into play, right? So in the same way that figuring out the length of a subinterval was important, once I find a patch, figuring out the magnitude of its area is going to be important. Figuring out all its nuances is going to be important. One way we like to do this also is using vectors to be a part of this description, because vectors are going to be very important in locating positions in 3D. And this is going to be something that we're going to talk about later on. So let's say I just took out one of these patches here and I just lay it flat on the page right here. And just imagine that there are vectors running along this edge, right? So I have a vector, let's call this vector A, and then I have another vector, let's call this vector B, right? So these are just vectors running along this patch. Here are some things I'm going to want to know. How can I find the area of this patch? Well, one way is to think of the patch as really two triangles. So here is our parallelogram. You can kind of slice it into parts. And so what we can do here is, if I look at this triangle, where the magnitude running along here is B, the magnitude running along here is A, and the angle here is theta, I can figure out the area of this triangle. And it's actually going to be half the area of the parallelogram that we actually care about. To move something out of the way here. Okay, so now we're in a situation where, okay, to talk about the area of this patch, I just need to be able to talk about the area of this triangle. Now, of course, trigonometry comes into play. We actually have a formula for that. The formula for the area of the triangle is, if you have a triangle like, so here's an angle, here's A, here's B, then we know that the area is, does anyone remember the area of a triangle if you know two sides and an included angle? Does anyone remember that? AB sine theta, exactly. So it's 1/2 AB sine theta, right? So in other words, the area of this parallelogram, the area of the patch, is going to be the magnitude of the vector A, the magnitude of the vector B, times sine of the included angle. So if I have a patch, if I know I can put vectors along the edge of the patch that I care about, and I know the angle between them, I can actually find the area of the patch by using this formula, magnitude of A, magnitude of B, sine theta. And now you might want to get into the situation of, well, how do we know what the theta is going to be? How can we figure out what theta is? And so now we have to worry about angles. And what we are going to do in this situation is, again, look at half the parallelogram. So cut off the top half, just connect the terminal points of A and B with another vector, cut off the top half. And we are going to, again, use trigonometry to figure out the angle. How can we actually compute the angle? Okay, so again, let's suppose this is A and this one is B. Now, based on this diagram and what we learned last time, what vector would be this? The vector that starts here and goes back there. See who was paying attention. What vector is on the other side? The resultant? How did we find A plus B? Remember, if I had A plus B, what that means is I went along A, and then I attached the tail of B there and go along B. So your A plus B should be a vector that's going like that. Right, so if that's A and that's B. That would be A plus B. So that vector is A plus B would actually be pointing up and to the right. It'll be the diagonal of the parallelogram. What is this vector here? C? I don't know what is C. You should be able to tell me in terms of A and B. B plus A is the same as A plus B. So that was, we did talk about that last time, I'm pretty sure. We had, yeah, A plus B is the same as B plus A. So if it's not A plus B, it's not going to be B plus A. Any other ideas? B minus A? That's getting closer. This one is actually A minus B, right? How would you know? Well, if you go along A and then you subtract B, which means you go in the opposite direction, then this new vector here going to the left, that is going to be A minus B. So that's the answer. This is actually the vector A minus B. Yes, the good old switcheroo. So you don't need to think of it, turn these into IJK, just by knowing what the geometrical interpretation of addition and subtraction is, that can get you guys to figure out. So, okay, so in order to figure out this angle, I'm going to look at this triangle. Now, of course, if I start looking at the lengths around the side, magnitude of A, magnitude of this, magnitude of that. So if I have a triangle where I actually know what is the length of all of these, let's suppose I know what the vector A is and the vector B is, how can I figure out the angle? Now, there is a nice theorem that can help us figure out the angle. This is the law of cosines, which most of you would have learned from high school trigonometry, and you guys, of course, do remember this, and I know you all do. But just in case, this is this is the law of cosines. So, and I know this isn't what you guys had in mind when you're like, how am I going to use this in my life? Oh, yeah, you're going to use this math in your life by using it to derive other math. Like, I mean, this is important otherwise, but here's one reason why you need to remember your high school geometry. Law of cosines is actually going to help us find the angle. So let's think of this theta as one of these angles here. This means, for example, I can use this kind of equation, like the top equation, to find the angle here. So in our patch above, using the law of cosines, what we would have is the following. So here I have a triangle where this side length is the magnitude of A, this side length is the magnitude of B, this side length here is the magnitude of A minus B, and I have an angle that's between A and B. So this tells us that the law of cosines says that the magnitude of A minus B squared is going to be equal to the magnitude of A squared plus the magnitude of B squared minus 2 times the magnitude of A times the magnitude of B times cosine of the angle theta, right? So you can think of your A minus B as the C here. You can even do that. Think of that as C. And then I'm using the last equation here. Yeah, it's actually a more general form of the Pythagoras' theorem. It's just, it works on triangles that are not right triangles. That's a way to think about it. Okay, so yeah, that is a way that we can find the angle. Now, of course, if I know A and B, these will be numbers that I can calculate, and then I can solve for the angle theta. So this is a way to actually figure out the angle theta. So this is actually an important equation right there. And we'll get back to this in this section. In fact, we'll actually get back to this. The area, Like this one here, which we derived above the area of the patch, we'll come back to that in the next section. Okay, so that's an idea the area idea we're gonna use in the next section, but the angle idea we're actually gonna use in this section moving forward. Now let's talk about direction. Now this is going to be an interesting one. So another thing we know from calculus that is very necessary is having a notion of direction. And for us in Calculus 1, this notion was basically the slope, right? So if you have some sort of line or curve and you want to talk about what direction is this thing moving in? Is it moving up? Is it moving down? Is it moving to the left? Is it moving to the right? That sort of thing. How we actually measure the direction or how something is slanting or moving is with the slope, right? So now the idea is, what is an equivalent idea to that? Can we actually talk about the slope in the same way that we used to do? How can we talk about how something is bending, right? So let's say I do have my patch in space. Okay, so this is my X, Y, and Z. And here's my patch hovering in space. Is there a way to talk about a certain direction that this thing is going in? So some of you might have seen cross products before, but let's make this a little bit interesting. Someone who's never seen this stuff before, right? So you have no idea what a cross product is. Maybe you don't even know much about vectors. Can you actually guess a way to talk about how this is slanting in space? Like, how would you describe it as a direction it's moving? So maybe you're looking for some sort of vector. Like, what vector would be useful? A diagonal in the patch? Well, that is an interesting first guess. It's the obvious guess. It turns out, however, that guess is actually wrong. Now, the question is, why is it wrong? Why is it the case that that is actually not useful in determining the area? In fact, it is actually useless, not even just the diagonal in the patch, but pretty much any vector that's parallel to the patch is going to be useless in determining the direction of the patch. Right, so let's actually just maybe illustrate this. Let's so here's where we would have really needed an in-person lecture. So here's the visualization. So this is my patch, which this is a great book, by the way. I actually like this book a lot. So this is the patch, right? So this flat piece of plane that's hovering in space. If you find the diagonal, let's say this is the diagonal vector, right? So the tip of my pen is the direction in which the vector is pointing. And you tell me, okay, I can put this diagonal along the patch that's running along the diagonal. And does that give me a unique identifier for the plane? The question is no, because that vector kind of would have the same property. It is also in the plane, but it's pointing in a completely different direction. That, right? See, this pen, I can move it along, like in the same plane as the patch in so many directions. There'll be an infinite number of possible vectors that can have that property. So it's actually not good enough to talk about something that's actually parallel. Now, you would realize that you might need a vector then that's not parallel to the plane. So now you might start thinking, okay, so there's going to be a vector that's poking out of this plane at some angle. And you might want to think, well, what is the right angle to use? Well, let's say someone guessed 30 degrees. I'm going to define the direction of this plane by something that pokes out of it at 30 degrees. Well, again, you run into the same problem. There are a bunch of vectors that poke out of this thing at 30 degrees. And you'll realize that you'll have the same problem with pretty much any angle that you can think of except one. The right angle, exactly. Once we determine a right angle to this patch, then it's pretty darn obvious what direction we're going to be talking about. The worst that it can get is that you would find the exact opposite direction, but that is really parallel anyway, right? It's going to be the negative of, it's either going to be this or the negative of that. And for most cases, it doesn't actually matter which of those you could pick. So if I tell you the perpendicular direction, I will uniquely identify the slant of this plane into the point where everyone on the planet is going to agree with me that this is the one that's going to work. Perhaps is opposite, but definitely that one. There's only going to be two guesses, not an infinite amount. And when it comes to defining something, you definitely want something where it's not, there aren't an infinite number of ways to define it. That's not very good. So it turns out when it comes to a patch, the best way to actually identify how it's slanted in space is to come up with a vector that is perpendicular to the patch. Now, such a vector that's perpendicular to something, this is what we call a normal vector. I don't know why they call it the normal vector, but being right angles at something is called being normal to the thing. So a vector that's useful would be the normal vector. So it turns out that that's going to be our guess. So let me share this again. So hopefully you guys saw that. Okay. Right? It doesn't sound normal. Yeah. So the idea is the normal vector. So one way to actually define direction is using a normal vector. This is a vector. Oh no, that's the thing that I mentioned to you guys. It's clapping for, there's a hashtag that goes along with this. Every day at 7 o'clock, they all cheer. You remember? You guys remember that? Yeah, so they're cheering for healthcare workers. Every day at 7, everyone claps and they go crazy and they play We Are the World and they blow air horns and everything. Yeah, it's a lot of guys going, woo! Sure, let's let's do it. But no, it's some, and I don't think we're my neighborhood is the only one that does it. Fireworks, that's new. Yeah, normal vector for the healthcare workers. Now, the word perpendicular itself is something that we're going to improve on. Right. So it turns out that this is the best direction to actually define how a patch or a plane is slanted. Okay, so that's another useful idea. So when it comes to dissecting things in 3 dimensions, there are a bunch of things that are important. One, the area of the patch, the angle that you can make between the vectors along the edge of the patch, and of course, the direction in which the patch is slanted in space. Okay. So now we have the idea of a normal vector. That's what it's called. That's just the proper name for it. So we want to talk about a normal vector to the surface, and we're going to discuss that in more detail in the next section. So what we want to do now is talk about, well, how would you even go about finding a normal vector, by the way? This is actually going to be very important. And I'll probably actually, so let me go back to this. So let's go back to the idea of finding normal vectors, ideologically speaking. Okay, so I have a vector perpendicular to this. The question is, how do I actually find that direction? Now, you might say, well, in this case, something parallel to the plane would work out. So I can find some other vector that's in the plane and just make sure that the vector that I have is perpendicular to that one, right? So first of all, we're going to need a way to measure how when two vectors are perpendicular. So that's one issue that's going to arise. But another issue that's going to arise is the fact that there's the same problem that we suffered from earlier, we're actually suffering from again, because how would you actually talk about what particular vector is going to be perpendicular to another one? So again, this is where our intuition from 2D fails us in 3D. Because in 2D, when you talk about one thing moving and something is perpendicular to that thing, there's really only one way to get that done. Pretty much, if I have a line and I know the slope is n and it's a non-parallel, it's a non-vertical line, then the only other line that is perpendicular to it, the only other possible slope is -1/n, right? The negative reciprocal. It turns out in 3 dimensions, this is no longer true. There is no longer only one slope that is perpendicular to a given slope. So here's my vector hovering in space. How do I find a vector perpendicular to that one? Well, this is one of them, but also this vector is perpendicular and that vector is perpendicular. Like I can have a vector meeting this at 90 degrees, moving all the way around this, and the relationship of being perpendicular is going to be the same, right? There's infinitely many, right? There's infinitely many directions. So if I only use one vector, there are going to be infinitely many vectors that are perpendicular to that one. So it turns out figuring out how something is perpendicular to a plane is another challenge that we have. Now, the trick, and I saw someone mention this in the chat earlier, is to use 2 vectors parallel to the plane. So here's the patch. If I have 2 vectors in that, what I can then do is find a third vector that is perpendicular to both of those vectors at the same time, right? So now I won't have the same issue, because you'll realize that yes, with one vector, all of these guys are perpendicular. However, if I put 2 vectors that I know lie in a plane that I care about, and I'm perpendicular to one, the moment I start twisting, it loses its perpendicularity to the other one. So if I can somehow use 2 vectors and get something that's perpendicular to both of them at the same time, that is the golden ticket, okay? So that leads us to this sort of situation. Let's go back to the OneNote. So that leads us to the, I had a picture of it, that guy. So that leads us to this guy. If I have a patch, right, and I know the angle between the 2 vectors and all that good stuff, I would want to find something that is perpendicular to both of them at the same time. That is going to be the way that I can guarantee that that thing is perpendicular to the patch itself, right? Because if I only have one vector in the patch, it's not useful enough, because there will be an infinite number of vectors that's perpendicular to that one that is at the same time not perpendicular to the plane. However, there is, again, and there's somewhat uniqueness here, because you can point in 2 directions really, but again, this gives you a more specific answer in the sense that most people would agree with this direction, either exactly or a scalar multiple of it. And so finding a vector that's perpendicular to 2 vectors at the same time is another thing that's going to be important to us, okay? So yeah, so that's some background there. That's some motivation. Why are we going to care? We're going to care about these things, right? Dissecting something into patches, finding the area of the patch, finding the angles that the patches move in, finding that's the angle, finding the direction in which the patch is slanted. All of these things are going to be important for us doing calculus. And most of this we're going to see in Calculus 3, but I want to kind of prime you for the ideas that you will need, okay? So hopefully that was clear to everyone. I know it's kind of weird watching it on the screen, but you guys can play around with books yourself, books and pencils yourself, and try to figure out that these things are. Yeah, so it was a lot. conceptually, I'll never actually test you on that, but I just want to give you somehow some intuition behind why we actually care about these things. Okay, so now what we're going to do is we're actually going to solve all of these problems, all of these things that I tell you we'll need to know. Be able to find the area of a patch in a very nice, neat, sophisticated way, being able to find the angle between two vectors, being able to find a vector that's perpendicular to two vectors at the same time. That's what we're going to cover right now. That's what we want to actually get into ultimately, right? The first thing brings us to the dot product. Okay, so let's talk about something called the dot product. Okay, so this is the guy where we're going to go back to finding the angle between two vectors, right? And I'm going to show you the calculations that we would go through in 2D to get this to work. But it will generalize to ND, and I'm just going to say it does. If you don't see it, you can actually work it out for like 3 dimensions, 4 dimensions, N dimensions, and the calculations should work out in pretty much the obvious way. So hopefully that's going to be clear. So let's actually figure out a nice way to talk about angles, especially if I'm giving 2 specific vectors. So let's say I'm given vectors in 2D. The vector A, which is A1, comma A2, and the vector B, which is B1, comma B2. How do I go about finding the angle in between them? Well, we saw earlier that the magnitude of A minus B squared is equal to the magnitude of A squared plus the magnitude of B squared minus 2 times the magnitude of A, magnitude of B, cosine theta, where theta is the angle between them. And normally we want the smaller angle, right? So theta is going to be somewhere between 0 and pi. So this we saw last time. This comes directly by the law of cosines. Now, let's get specific. What would this actually look like? Well, this is the vector A1 minus B1, comma, A2 minus B2 squared. This would be A1, A2 magnitude squared plus B1, B2 magnitude squared minus, let's move something out the way here, minus 2 times the magnitude of A1, A2, B1, B2 times cosine. Well, this I actually don't need. I'm going to leave these here. I don't need to write those out, so I'm going to leave those here. I'm going to leave this as the magnitude of A, magnitude of B, cosine theta. Because the version I want is going to be nice to leave those. So what is this going to be? Well, this is going to be this squared plus that squared, square rooted, but then I squared, so the square root is going to go away. So this is going to be A1 squared minus 2A1B1 plus B1 squared plus A2 squared minus 2A2B2 plus B2 squared. That is going to be equal to A1 squared plus A2 squared plus B1 squared plus B2 squared minus 2 times the magnitude of A, magnitude of B, cosine theta. Now what you'll notice is that I can subtract this from both sides. I can subtract B1 squared from both sides. I can subtract A2 squared from both sides. I can subtract B2 squared from both sides. And I can actually solve for, say, the cosine of theta, which ultimately will help me to find theta itself. In fact, I will now be able to say that my cosine theta, and again, I'll be able to actually cancel the 2's from everybody just by dividing by 2's. So my cosine theta is going to be this guy. Let's see who is left over. The A1B1 plus the A2B2 divided by the magnitude of A, magnitude of B. Okay, so this is an equation that's going to be important. If I need to find the angle, I just take the cosine inverse of this expression. Now, if this had more things in them, not just two things, the calculations would work out very similarly. They'll work out almost to be the same, same format. So if I had n dimensions, right? So A1, A2, all the way up to AN, and B1, B2, all the way up to BN. The top part here is actually going to look like this. It's just going to be a sum of all the A subscript with their corresponding B subscripts added together. So what you'll notice is that this expression here this is an important expression. It's also very nice, very poetic, very elegant. You kind of see it's just the product of both of all the corresponding components of the vectors, and then you add them together. And whenever we see something nice like that, we like to give it a new definition, right? So this expression, the sum of the products of corresponding components, will make that into a new definition, and that is what we call the dot product. So that's the definition. Given two vectors, of course they are in Rn, they are n-dimensional vectors. We define the dot product, sometimes we call it A dot B, to be this expression. Multiply the corresponding components, add them together. We denote this by A dot B. You literally put a dot, right? So now you have to be careful when you're talking about vectors and how you're denoting multiplication. Multiplication of vectors really isn't a thing in the strictest sense, at least not for us. There is something called a dot product, which you literally write a dot to denote that. If I write a vector A dot vector B, what it means is to do this. Take the product of corresponding components and add them together. Why is that important? Well, it's an expression that's going to show up once I try to find the angle between the two vectors. And it's always going to be that expression that shows up. Also, now what you realize is that I can actually rewrite this thing as cosine of theta is equal to A dot B divided by the magnitude of A, magnitude of B. And then that leads me to this box right here. One way to express the dot product in terms of the angle between the two vectors is to actually take the magnitude of A, the magnitude of B, times cosine of the angle theta that's between them. So that's a theorem, and we proved it. Technically, the proof is up here. It's not very hard to show. But that is the dot product. This is its definition. This is a property that it will obey. And another thing that I want you to note here, the dot product is a scalar. Now I do realize that me typing that in all caps with all these exclamation signs and making that in red seems a little bit aggressive. And you might say, calm down, Jhevon, why are you getting so excited about this statement? But I've been teaching a long time. I've seen almost every mistake that that a student could possibly make. I mean, sure, occasionally these days, students do show me mistakes that I never could have imagined someone doing. But for the most part, I've seen it all. And as you can probably guess from that, there's a reason that I am putting this in all caps in red and underlining it and putting all these exclamation marks. The dot product is a scalar. The dot product is a scalar. I take two vectors and I can combine them. I can take the dot product of the two vectors, and the result of that operation is going to be a scalar. So for example, if I have a vector 1, 2, and I have another vector -3, 5, and I talk about what is the dot product of these two vectors. Well, it's going to be 1 times -3, because that's the A1 times the B1, plus the 2 times the 5. You will notice that that is 7. This is a scalar. So when I take two vectors and I find the dot product of those two vectors, the answer is going to be a number. It's going to, for us, it's going to be a real number because your components of our vectors are always going to be real numbers. So it will always be a scalar. A dot product is a scalar. Yes, it involves us using vectors, but the output of the dot product is a scalar. That is very, very important. Is it? So I would like everyone to repeat after me. The dot product is a scalar. The dot product is a scalar. The dot product is a scalar. Say that 3 times when you go to bed, and it will keep all the monsters away. The dot product is a scalar. It is not a vector. And when we get to the next section, it's going to be even more important to remember that. Okay. So there are some more things to note. These are the properties of the dot product. Now, based on the definition, you can actually prove these. Yeah, exactly. that is, yeah, that has happened, as Kevin says. There are times when I would actually write out in a quiz, what kind of an object is the dot product? Circle one, scalar or vector, and you would think that everyone would have circled scalar because no, it happens. Okay, so the dot product is a scalar. It's important for more reasons than a quiz. But here are some other properties, and you can figure these out by straight up using the definition. So I'm not even going to go over it. Those are things that you can prove. And the definition, again, kind of tells you, you can see why some of these are true. Because it's really just an expression that's a product, and you can flip the products around and you can flip the sums around. So a lot of just basic arithmetic rules with the real numbers can tell you that these products are going to be true. So you can even try some of them. Your homework might actually ask you to prove some of them. This works in higher than 3 dimensions. I mean, this states specifically for 3, but it does work in higher than 3. The dot product will work in higher dimensions as well. Other things I want you to note. Remember, we can talk about the dot product in terms of the angle in between the vectors. This gives you an interesting case. If your angle is pi over 2, then that means your 2 vectors will actually be perpendicular, right? Because they would meet at right angles. One thing you'll notice is that, of course, the cosine of pi over 2 is 0. So you get to the conclusion that if the dot product of 2 vectors is 0, then it happens if and only if they are perpendicular. Now, the word perpendicular, as I mentioned here, we'll actually use that. We're actually going to talk about this word perpendicular. The word perpendicular isn't good enough anymore. And why isn't good enough? Well, I already showed you. Perpendicular, as we understand it in 2D, is just not sufficient. Perpendicular in 2D is if there's only one direction that would be perpendicular to some other direction. In 3D, this is not the case. In 3D, you can have perpendicular with infinite variety. So we want to call this by a different name just to emphasize that it's a whole other level, right? So we call that orthogonal, right? So this is the new word now. This is the new vocabulary word. Orthogonal means exactly the same thing as the word perpendicular. So orthogonal is perpendicular in 2D, but once you're in 3D or higher, the phrase used is orthogonal because it's bigger than what perpendicular usually describes. So we want it in the same way. If I say two vectors are orthogonal, it means that they're normal to each other. Or I can say that the normal vector to a plane is orthogonal to the plane. Yeah, so you essentially now just always call it orthogonal. Like it's right even in 2D, but perpendicular is just, it's not good enough. So in the same way that we normally use slope for a straight line, but once we talk about something that's not a straight line, we use the word derivative. Derivative is literally a synonym for slope. But we use this whole other phraseology to show that this is a lot more comprehensive. It's a bigger idea than just slope. We normally use slope for straight lines. You want to talk about slope in general, you say, quote unquote, derivative. In the same way, perpendicular, that's a thing that we live in. The people in 2D call it perpendicular. Now we're on a higher level, we're on a higher dimension, we're all the way up in 3D. We call it something else. The people running around in 2D think of it as perpendicular. We know that it's orthogonal. Orthogonal means perpendicular in just a multi-dimensional sense. Yeah, to low, to low levels. Okay, so that leads us to a definition slash proposition slash theorem. Technically, you can prove that just by plugging into this formula over here, but it's also useful to take it as a definition. You can actually define this to be the case because it'll always be true. If you have a dot product of two vectors giving you the zero vector, then they are perpendicular. And if they're perpendicular, then their dot product will be not, see, like I just called myself, the zero scalar. This is a scalar. Notice that there's no arrow over the zero here. So if the dot product is a zero scalar, that means the vectors involved are perpendicular. So this gives us a new mantra. So in the same way, that which is over here. So in the same way that we just know from the 2D case, okay, this slope is perpendicular to that slope if they're the negative reciprocals, right? Now we just know a different way to talk about perpendicular. This vector is perpendicular to that vector, namely orthogonal, that's what we call it, if the dot product is zero. We also know it's parallel if one vector is a scalar multiple of another vector. So we know that two lines are parallel if they have the same slope, and they're perpendicular if one slope is the negative reciprocal of the other, provided that neither of them are vertical. In the same way now, we have these two new ideas that we take in the same vein in 3 dimensions. Two vectors are parallel if one is the scalar multiple of the other. And the two vectors are orthogonal, aka perpendicular, if their dot product is the zero scalar. So a dot product is a scalar, and there's one scalar in particular that is very important, the zero scalar. Dot product is zero means perpendicular. Okay, that's at the end of the day, that's what you want to take from this. C is a constant, yes. So it's a scalar multiple. This was mentioned in the last lecture, so it's on the other page. Okay, what else? That's almost all I want to talk about, dot products, but do I want to talk about that now? Let's do some examples. For now, let's actually take these guys. And we will move them. Let's say we'll move them to a new page. Forget it. Okay, let's just. Okay. Those guys don't move that. Maybe I'll just move these guys and we'll come back to those guys. Okay. We'll talk about projections later. Okay, let's actually do some examples. Yeah, it's both a blessing and a pain. When it comes to math, it's always a pain. The chalkboard rules supreme. It always has and always will. Okay, so let's just go into some examples. Here's two vectors, vector 1, 2, 3, and B is the vector 1, 0, -2. Find the dot product and find the smallest angle in between A and B. So let's actually do this. So A, and it's doing it again. Hold on. I'm going to restart OneNote because sometimes that fixes the issues. So you guys can all see the screen again, right? Okay, A, all right, A dot B. You always actually write the dot. It's important. Don't just write the A and the B beside each other. It's important that you write the dot. It's called a dot product. Okay, so this is just 1, 2, 3, dot 1, 0, -2. And this is just the sum of the products of corresponding components. So this is going to be 1 times 1 plus 2 times 0 plus 3 times -2. In other words, that's 1 plus 0 minus 6. This is -5. Now, there is some interpretation as to what that would mean, but it's more of linear algebra stuff. Let's not talk about that. The only important interpretation, the only important scalar for us is going to be the 0 scalar. That has a very important interpretation. It would mean that the vectors are perpendicular. What I can say about these is that these two are not orthogonal, right? Because their dot product is not 0. So however these guys look in space, they do not meet at right angles. What is the angle that they meet at? How do we go about finding that? Well, we're a little bit short on time, so let's actually just go into it. We know that the cosine of the angle is going to be A dot B divided by the magnitude of A, magnitude of B. So this is going to be -5 divided by the magnitude of A. That's 9 plus 4 plus 1. That's radical 14. And the magnitude of B, which is going to be 9 plus, the B. Magnitude of B is 4 plus 1. It's radical 5. And so this means our angle between them is going to be the cosine inverse of -5 over radical 14 radical 5. So that would be your answer. In case you're wondering what that is, let's see. Let's go to good old Wolfram. Arc cosine of -5 divided by the square root 14 times 5. And that's about 2.21 radians. Yeah, no, that'll be the smallest one. So of course, whatever these vectors look like, this is in here is going to be 2.21 radians. The other angle, this is the larger angle, that would be 2 pi minus 2.21. So this is our theta over here. If that's your A and that's your B. Okay, so that is the angle between the vectors. To another example. Okay, so show that these two are orthogonal, right? Meaning whatever they look like, I'm not going to draw them and use like a compass, use all these geometric shapes to figure out if they're orthogonal. All I need to do is just find their dot product. This is going to be 1 times -5 plus 3 times 0 plus 5 times 1. And that is 0. The vectors are orthogonal. So that's that. Find the dot product if you know the magnitude of A, the magnitude of B, and that your angle is pi/4. So this is just testing your knowledge of the fact that you know that A dot B is going to be A B cosine theta, which is something that we used earlier. This means that A dot B is going to be 2 times 3 times cosine of pi/4, which you know cosine of pi/4 is radical 2/2, so that's just 3√2. What other examples did we have? So as you can see, I mean, we were talking about some pretty heady stuff earlier, but that wasn't the area equation. That was the angle equation. The area equation has sine theta in it. Okay, well, this one is just 2D. Find a non-zero vector B that's orthogonal to A. In 2D, this is actually pretty straightforward in the sense that there's not many candidates. If you want to make sure that the dot product of this with that is 0, you can choose B to be, you swap the components, and then you make one negative, or something like that. Either of those will work. Then if you take A1, comma A2 and dot product it with minus A2, comma A1, that's going to be minus A1, A2 plus A1, A2. So sometimes you can actually see this pattern, or you could have just actually guessed it. Set B equals B1, B2. We want A1, A2 equals B1, B2. Dot product with B1, B2 to be equal to 0. So this tells you that you would want A1, B1 plus A2, B2 to be 0. And so if I just pick this one to be the negative of that and this one to be that, that will give it. In fact, any constant times this would actually work. But why make it any more complicated? Right? All right. That's just something to look over. But of course, the first 3 examples, these are the ones that you really should know how to do. Just being able to compute a dot product, straightforward, find the angle between 2 vectors, be able to tell if something is orthogonal or not. And I don't know, I might ask something like this, but probably not. Yeah, those are some examples. Other things that are important. Is vector and scalar projections. Now that works. I mean, I have some space I want to clean up here, but. I'll worry about that later. Okay, so another thing you want to talk about here is vector and scalar projections. Now, projections are super important. They're important in physics and linear algebra and geometry, all over the place. And what these are is sometimes I can have two vectors, like a vector A and a vector B. And what I want to do is I can just pretend like I'm shining a light here and project vertically down one vector on the other. So like I'm projecting the shadow of this vector onto the other vector. And knowing what this new vector is, which is the red vector here, as well as knowing what its magnitude is going to be important in a multitude of contexts. Projections are used all over the place. And you'll use them in physics, and in Calc 3, you'll actually use projections to derive a lot of things. You might even see some things, I'm not sure if the homework actually asks you to use projections here, but you might see some applications of projections in your homework. Now, this vector here is, of course, parallel to the vector A. So this is going to be a scalar multiple of A, right? We'll worry about what that scalar is. Of course, the scalar multiple of A is going to be whatever this length is. So the scalar, the length of this, we can figure that out using trigonometry if we know that the angle is here. So if this is a right triangle, this is the length B. We don't need to know this length. We know that the cosine is the adjacent over the hypotenuse. So the length of this part here is going to be the magnitude of B cosine theta. So we know that the length of the shadow is equal to the magnitude of B cosine theta. You could do this trick where we multiply and divide by the magnitude of A, and that would give us in the top A dot B by formula over the magnitude of A, right? That's going to be this formula that's right here, right? That's how they figured that out, okay? Now, of course, to find the vector here, I'm just going to take that magnitude and multiply by A. So it scales the vector A to be this length. And so that's what I do here. So I just take this length and I multiply it by the unit vector. So here's where a unit vector comes up, because I want to make sure that the length of the vector I get is this. So I take a unit vector in the direction of A, multiply it by this length, and that will give me a length, a vector that runs along A with this particular length. Of course, I can simplify this formula and it would actually look like that. Notice that this here will be the vector, while this magnitude here will be the scalar. They are called, therefore, correspondingly, the scalar projection, which is the length of the shadow, and the vector projection, which is the actual vector that runs along the shadow, right? This is often called, the length of the shadow is often called the component of B onto A. So that's the idea. I have a vector B and a vector A. If I project the shadow of B onto A, the length of that shadow is the component of B onto A, and that's the formula. The actual vector that runs along the shadow, this is called the vector projection of B onto A, and it has this formula. So as an example, let's say I have two vectors here. I have a vector B. I have a vector B, and I have a vector A, which are these guys here. What I want to do is I want to project in a perpendicular fashion the vector B projected it onto A. So that vector is going to be the projection of B onto A, and its length is the component of B onto A. How do you go about finding this vector? Well, you actually just use these formulas that I just gave you here. So find the vector and scalar projections of this vector onto that vector. What is this red vector in this situation? So the scalar projection well, this is going to be the component of B projected onto A. That is just going to be A dot B divided by the magnitude of A. This is going to be 3, 0, 1, dot product with 1, minus 1, 2, over the magnitude of 3, 0, 1. So this is just going to be 3 plus 2 over radical 10. So this is just 5 over radical 10. So that's the length of this vector. Now, if I want to find the vector projection, what is that actual vector, the red vector? This is called the projection of B onto A. This is going to be the guy that has this length times, I don't want to put a dot. I have to be careful how we use dots now. Times the vector in the direction of A, that's a unit vector. So this is going to be, well, we already know that that's 5 over radical 10. And then we're going to multiply this by 301 over the magnitude of 301. And so this is 15, 0, 5 divided by 10. So that's going to be the vector 1.5, 0, 0.5. Or actually you prefer fractions, 3 over 2, 0, 1 over 2. So that's the actual vector here. And that's all about, that's all we want to know about dot products, which, yes, no, the length of A over magnitude of A, the length of this vector is 1. The vector itself isn't 1. So A is a vector, this is a scalar. So I just want a vector that has the same direction as A, but has length 1, so that when I multiply it by this number, it scales that length to the length of the component. Now, that actually took a lot longer than I thought it would. I thought we would get through cross product today, which is a whole other beast. It's going to be really fun stuff. Yeah, that took a while. So you guys have survived without learning about the cross product today. That is, we're going to stop here because I'm pretty sure we're out of time. Cross product is where it gets more interesting. Yeah. Like I said, with the exam, I'll post a mock exam, so you'll know exactly how many questions and everything. So don't worry about it. But yeah, that's our dot product. So these were the important ideas that we wanted to actually learn about. And the dot product actually tackles one of them. The cross product is the guy that's going to tackle this problem. Figuring out the area here, as well as being able to find the perpendicular vector. The cross product is going to help us with that scenario. And you're going to find that it is actually useful in a lot bigger context than that as well. Yeah, so the first test is up to section 10.10. And as always, I'll post a PDF of this for you guys with the lecture here. Well, yeah, the PDFs of the notes is usually posted in the description box. I always post it in the description box of the YouTube video. Scroll down to the last question. The vector projection question, or? So this was the last question, which it'll be posted tonight. Find the vector and scalar projections of B onto A. Was the last question we answered. Yeah, I don't know. I said, well, I know. I would say I probably got a little bit carried away just explaining all this stuff with my textbook and all these pens, but I really don't think the few minutes I spent doing that, I would have been able to cover an entire different section. Look at this. The cross product is a vector. Okay. Anyway, we will cover the cross product in the next lecture. Stay posted for the test, as well as some more information on it. I will post that for you guys. Until then, we're going to wrap up here. Hopefully you guys could have followed. So yeah, that's it. That's all we're doing for tonight. Take care, everyone. Enjoy your night. And I will see you guys in the next one. So, ciao.